welcome to this Learning Machine seminar, everybody, and especially Divia Grover, who is our guest today and our speaker. Divya is a PhD candidate at Chalmers University of Technology here in Gothenburg, and the talk is going to be about sample-efficient Bayesian reinforcement learning.
Okay, great. So hello, everyone. Welcome to this presentation, which will be an introduction on Bayesian reinforcement learning. And if we have time, then I will give the contributions that we made. The title of this presentation is Sample Efficient Bayesian Reinforcement Learning. I am Divia Grover. I am a PhD student at Chalmers University for quite some time now. And okay, so let's get started. So the motivation here I will give for those uninitiated is this game of Pac-Man. So you have an agent, quote unquote, the yellow Pac-Man, and the objective of the Pac-Man is to collect the white balls, that's like its food, and at the same time avoid the ghosts that are in different colors. So what happens is that we can imagine that this is a typical scenario of an agent acting in an environment where the agent is the yellow Pac-Man, and there is certain states associated with the environment. So when I call a state, so I mean that you can take any screenshot at any time of this game, for example, right now. So this is a state of the environment. So it involves all the locations of the ghost and where the location of the agent itself, and where are the possible food locations. So all this information is called collectively the state of the environment. Okay. So goal of this agent is to act optimally or beneficially for itself in this environment. So going to the outline of the presentation, I will first briefly describe what is the sequential decision making, because reinforcement learning and every other type of agents acting under environment comes under the broad umbrella of sequential decision making. Then I will discuss the particular model that we will be using, which is Markov decision process, and we will be solving that. After which I will increase the complexity a bit and explain what is reinforcement learning and specifically what is Bayesian reinforcement learning. And then I will give the main model of today's talk, which is just an extension of Markov decision process. So it's called Bayes Adaptive Markov Decision Process, or BAMDP. And then I will summarize how to solve, how is the classical way to solve it, and some of the related work. And if we have time, we will move forward to the contribution that we did in the last year as a paper, and then discuss some results. But the main idea of this talk is to be a tutorial on Bayesian reinforcement learning. So the first section is more important. Okay, so what is sequential decision making? So the basics, as I explained, you have an agent that is trying to act optimally in an environment, and the actions of this agent will have certain feedback. So for example, the Pac-Man, when it was eating the white balls are no longer there. So that's like a feedback of the actions of the agent. And in sequential decision making, there are basically two types of uncertainty. The first type of uncertainty is uncertainty of the environment itself. So for example, if the agent tries to act from a particular state and with the same action, the environment will be static and the feedback will not always be the same. So it may be that the agent will slip. For example, the Pac-Man in the previous game has a slip probability. So if it tries to move left, it doesn't move left completely. So that's a feedback of the environment, which is stochastic. And the type 2 uncertainty is much harder, which is called lack of knowledge about the environment. So this uncertainty is basically uncertainty about the stochasticity itself. So the agent is completely unaware of the environment. And I will basically incrementally show you how to deal with the two types of uncertainty. The second one being also being also called as reinforcement learning. But first we'll start with type 1 uncertainty, that is inherent to the environment itself. But before we do that, the main focus of sequential decision making is always planning. So to plan actions. So when I say planning, I say that planning is the process of deciding long-term actions that the agent wants to execute. So we will formulate first the mathematical model for the first type of uncertainty, which is type 1. So we will define what is called a Markov decision process. So it's a mathematical model that consists of three major elements. So the state and action sets defined by capital S and capital A. And by subscript, when I say ST or AT, I denote the subscript as the time, because this is a sequential process. So ST is the current state of the environment and the agent itself, all the all-inclusive information. And AT is the action that the agent will take. So at time t, the agent takes AT, and the environment transitions from, or we can say transitions from ST to ST plus 1, and the environment gives a feedback to the agent, which is in terms of the new state and what we call the reward. So if the agent took, let's say, the correct action or no, so this is subscripted by time t plus 1. So this is the essentially the loop that happens when an agent acts sequentially in an environment. And essentially S and A come from some sets, and R T, we say that it comes from 0 and 1. The main part here about the stochasticity or type 1 uncertainty is captured by the probability distribution, which is called the transition distribution. So here I denote by P a probability distribution of seeing a particular next state value at the next time step, given the current state and the action that the agent took. Okay. And this, the subscript here, probably mu simply means that this is for a fixed MDP mu. So I just have an MDP mu for now, but later in reinforcement learning, we will even have some uncertainty about mu. But for now, it just means that given that there is a particular state and the agent decides to act at certain with a certain action, even then there is a certain uncertainty of what the next state will be. So that's the type 1 uncertainty. And this is captured by the transition probability. Similarly, we have a definition of reward function or reward distribution. And to make things more even concrete, I will give you an example here. This is a 3-state MDP. So you have states S0, S1, and S2. So let's say the agent is at S0, it takes action A. So based on the transition probabilities, it are demarked by the arrow. So it says that from S0 with action A, there is a 50% chance that the agent will land again into S0, and 25% chance each that it will go to S1 or S2. And this thing over here is just essentially saying that the reward probability of seeing a reward valued 1 is 0.7%. So that's like a small MDP for an example. And this is the mathematical model you need to solve first before you can proceed to something more complicated, which is reinforcement learning, where you don't even know the MDP mu. So we will discuss that later. So essentially MDP. So to make things more formal, what we want to find is a policy. Policy is an algorithm for selecting actions. And essentially in this MDP, what we want to maximize is the sum of rewards. So here, if you forget about this gamma over here, what you see is the sum of rewards, RT. So RT being from 1 to capital T, the sum of reward. But this gamma essentially is just a weighting factor that just says that we weight, because this is between 0 and 1, so it weights the rewards that you receive sooner much more than what you receive later. And to maximize this sum, we define this sum in another way. We call this sum as a value function. So the superscript is just fixing for a particular policy. So the value function for a particular policy, pi, and a particular MDP mu from time small t to capital T is essentially the sum of the rewards starting at a particular state S at time t. So this is the value function, or which is essentially the sum. And the expectation is over all uncertainties that is coming due to the transition and reward distributions that I defined before. And in the limit of value function, we say that if the agent is acting for a long time in the environment, then essentially you take the capital T to be infinity. So this is the main, basically the formulation of MDP. But now we need to solve this MDP. So how you do that is you essentially open up this term. So this is again the sum of rewards. So k from 1 to infinity, starting from a particular value S for a particular policy and a fixed mu. So you can just consider them that they are fixed now. So we just focus on the sum inside. So you can break the sum into the immediate reward R1 and everything else. Okay, conditioned on that the start. Okay, now you can condition on the fact that the next state is S prime, the immediately the step two state. So so essentially you divide this term into two parts, and you can just by the sum of expectations, you can just say that this is the expectation of the immediate reward plus the value function of seeing a particular next state which is weighted by the probability of the next states, because you know that the environment feedback, the next state, is also stochastic due to the transition distribution. So we are just weighting the value function of each possible next states that we can see by their own probabilities of seeing them for a fixed policy and a fixed MDP. So for now, everything is fixed, like policy and MDP. So this is a recursive definition, and this is also known as the Bellman operator because it allows us to recoup the value function if we know the value functions in the future. So essentially, this is the B pi mu is the Bellman operator for a fixed policy and a fixed MDP, which takes the value function at time in the future, time t plus 1, and plugs that on the right hand side of the equation and will give you the value function at time t. Essentially this line over here at the bottom left. So you have a value function of a particular policy and a mu at time t, which is essentially calculated by applying the Bellman operator on the value function of the future, on the future value functions. And this is the way you can calculate the value function in an MDP. Visually, it is much more easier because if you have any background in general AI and like something like zero-sum games, you know there are some algorithms called like A star or tree search or minimax algorithm. So similar to that, this backward induction can be visualized as a tree. And by that I mean is that at time t plus 1 for different states. So the superscript here is for different possible values of states. So S1 to N. At time t plus 2, assume that you know the value function. Okay, so you know the value function in the future of the future at time t plus 2 for this particular policy. Then you just have to plug it in over here, and it's essentially just doing an expectation and calculating the value function at particular time. At particular time st plus 1. Sorry, so from t plus 1 we from t plus 2 we came to t plus 1, and it is doing that for all possible states. So the superscript here is different possible states. So you do that for all possible states by plugging the value at t plus 2 to calculate the value at t plus 1. So now you have this sequence, so this vector, and you can repeat that again until time t. So essentially what you have is a tree. You start from the leaf nodes because you have information at the leaf nodes, and you propagate it back to the root. So if you just imagine this horizontal in a vertical tree, so this basically the leftmost node is the state st, and the value function here is essentially the value at the root. Okay, so this is what we call the planning tree. And what I showed before was for a particular action, because here the actions are just one based on the policy pi. So this superscript is fixed, but we can do that same for policy optimization. So optimal value policy is optimal value function is basically the value function for all possible policies, the maximum value function. And the optimal policy is the particular policy. So you can do this tree search kind of thing even to calculate the basically the best action at the root. So for a long horizon, you can calculate what should be the best action that you have to take at the root st. And how you do it by is building this expectimax tree, as I was saying to you. So let's say you have values here. These are two possible actions that you can take from this particular node. So you do a max here, and that becomes the value. So you calculate the expected value based on the particular action, and that becomes this particular action's value. And so for this one, and between these two actions, you do a max operator and you calculate and then you get the value function at this particular node. And then you again do an expectation for this node. So all the child nodes values will be summed up in an expected way, and you get the value function at this action. And between these two actions, you choose the one which is max at the root. So this is like an expectimax tree, which is also used in like zero-sum games to calculate if you have like a chess or something like classical chess algorithm. So why I showed you all of this is because this is important and we will build upon this. So until now, what I showed you is sequential decision making is nothing but planning long-term actions by the agent. There are two types of uncertainty. One is inherent and other one is the lack of knowledge about the environment. So inherent is because in the MDP model, the agent is aware, or you can say the algorithm that you have is aware of the transition distributions, but it has to do some extra computations. But still, the uncertainty is inherent only in the environment. So the next state is probabilistic, but you know the probability distribution. So this is the type 1. Now next one will be the lack of knowledge about the environment. That's basically RL. So that we will discuss in a moment. But if you know the MDP model, the mathematical model, you can do backward induction, and backward induction is nothing but tree style computations. Okay. So now we discuss the main part of reinforcement learning, that is lack of knowledge of the environment. So I will first give you an intuition. So in sequential decision making, this is also known as the lack of knowledge of the environment is also known as exploitation dilemma. So what happens is you can see from the cartoons here. So the guy doesn't have any information of what their objective is. So he says to his assistant that just collect all the information and we'll think what we can do later. But at the end, when they are having a discussion, they are saying after analyzing all the data, I think it's none of the information that we collected was useful. So what happens here is the agent is now unaware of the probability distributions in the MDP. And that is the type 2 uncertainty, lack of knowledge about the environment. I will make this more concrete in a bit. But the dilemma here is, do you collect information that ultimately is not useful to improve your, to improve your sequence of actions? So that information is essentially useless. So how do you choose if you need more information or you simply do with what you have? Okay. So I'll give you an example of reinforcement learning. So here we have an agent that starts at the bottom left at the start state, okay, at the corners. The goal is to collect the golds, and the agent, if it falls in the blue water, it will drown, so it cannot move. But the problem of this agent now is that it doesn't know if it is in environment 1 on the left or environment 2 on the right. Okay, he will start. So let's say he is blind. So if he starts at the bottom left start corner, so if the agent goes top, and if he is not aware that this is environment 1, then he will drown instantly. But here it's safe to take the action going upwards. So that's like the problem of not knowing the environment by the agent. That was not the case before. And so we will discuss what is the formulation exactly mathematically. So let's recall, when I discussed planning for MDP or deciding what's the best action, I told you that there is a fixed mu, which is an MDP. So it has the state set and action sets. That's like trivial. But the main important part is that you have access to these probability distributions of the environment. So if the agent, if the environment is at state ST and the agent takes action AT, so there is an uncertainty of what this next state will be, but still the agent or the algorithm has access to this P mu. Okay. So that's planning. And for planning under that conditions, you can have exact or approximate. I gave you one example of exact tree computation. And what you do is you calculate the maximum policy, the maximizing policy for the value function. But now what is planning for RL? In the RL, you essentially don't know mu, or you can say you don't have access to these probability distributions of a transition and reward. Then what should we do? So so there are multiple approaches to reinforcement learning. The Bayesian approach says that, okay, we don't know the MDP mu. So what we do is we assume a distribution over certain set M. So we say that the MDP belongs to certain set M, or more exactly, these probability distributions are within certain, there are certain probability distributions that can only occur. And then we have a distribution over these distributions. So essentially, we have a beta distribution over each MDP in the set M. And this is our belief of what the MDP will be. And then what we do is we basically maximize the objective function, which is basically the value function weighted by the belief of the agent of particular MDP. Okay. So this is like a weighted value function maximization objective. So we tweak the value function a bit, and we just assume that since we don't know the MDP, the agent will maintain a belief over all possible MDPs mu. Okay. So to make things more concrete, yeah.
A quick question, if I can interrupt.
Yeah.
Just quickly, I mean, sometimes you differentiate between noisy environments versus noisy actions. So in your particular examples that you're going towards now, do you kind of equate noisy actions to be the same thing as a noisy state space?
Yeah, yes. The policy space is as large as possible. So it consists of all noisy, even the noisy actions. But the fact is that for MDPs, we don't need noisy actions. And for the next thing that I will be talking about, everything is inclusive. So you can consider the policy space as large as possible.
That's not what I meant. It was more, I mean, there are a few environments where, for example, your agent tells makes the decision to go right, but what happens in the end is that it actually goes left. So there's noise in the actions themselves and not in the environment.
Yeah, but okay. So in that case, I consider that inside the environment. Yeah.
Okay. All right. Thank you.
Yeah.
Maybe can I ask a quick question?
Yeah.
So you mentioned, I mean, for the first case here, like, you gave the example of this tree based, like, when we go from the leaves to the root.
Yeah.
Can we say that, I mean, like, for the second problem, like, where the mu is unknown, that actually the tree structure is changed, or that the probabilities are changed, or maybe different than that one? I mean,
yeah, exactly. Yeah, that's what we still have, this tree kind of structure, but the transition probabilities will change, and some small elements will change in that tree structure. You're right. Yeah.
Thanks.
Okay, so as I was saying, what happens now is I gave this algorithm of trees, tree style algorithm, is because it's like it's the same algorithm that we will use when the mu is unknown. And as I was telling just now, that certain elements in the tree will change, and that's what I'm going to discuss now. So before that, let's go to the intuition. So as I said, there are two. So this is the case of an example where there are two environments, and I say something about the belief. So I said I maintain a belief of the mu's. So here there are two mu's, mu1 and mu2, environment 1 and environment 2. And we maintain a belief at the start. So the agent is at the start, but he still doesn't know in which particular environment he is. So there is a belief that he maintains, and he says that I am 50-50, like 50% chance that I'm in environment 1 and 50% chance that I'm in environment 2. And then he updates the belief, or his own belief, about the using the Bayes rule mathematically. But essentially what happens is that, let's say the agent decides to go towards the top, towards up, and the agent doesn't experience any drowning, so he's still alive. So instantly he can update his belief to probabilities of being in this environment to 0 and probability of being in this environment to 1, right? Because he's still alive. I mean, he didn't drown. So the belief that was at the start state 50-50, 0.5 has changed to 0 for this one probability, and 1 for this one, because he has safely moved to this square. So that's kind of a way of him to know at each action, he can be more certain that between these two environments, which one he is in. So he will update his belief as well in this process. So you can just think of the belief as a summary of the history of the experiences that the agent has when he's acting. Mathematically, this is updated simply by the Bayes rule. So the Bayes rule simply says that the posterior of any element here, or any variable, random variable mu, is essentially the data likelihood. So for us, the data is the reward and the states. So it's the data likelihood times the prior. So it's essentially prior times likelihood, and that's proportional to the posterior. So at each step that the agent takes, right, up, he's updating his posterior as well. So here the objective function changes a bit. So that's what the tree structure will reflect. Okay. So now BAMDP is essentially a Bayes adaptive MDP. So the first thing I will say is the state says ST, and the action set and the reward and the discount, all of them are same to the underlying MDP that it's an extension of. So the state set remains ST, but here we will define a broader state set. So what the state here will be called is an information state. So it will be a tuple of the state of the agent as well as his current belief, which is also subscripted by T, because as the subscript changes, his belief will also change by the Bayes rule. So what we denote here in BAMDP is this information state or augmented state space, which is the state and the belief as well. And similarly, we define transition distribution and reward distribution from the MDP. So we just basically say that the transition distribution of going to the next information state, given the current information state and the action, is essentially just the marginal weight, just the marginal. So essentially, we are saying that probability. So this is the transition of distribution of the underlying MDP for a fixed MDP, and then we weighted by the basically belief of the MDP that we have at time t. So it's essentially the marginal distribution. So this is the transition, and reward is also defined in a similar way. So you can just say you just average out the transition probabilities by weighting them with the beliefs that you have now for each possible environment or mu. So that's how you build up your transition and reward distributions. And you will have a similar expected max tree as you had before, just that the STs nodes are replaced by omega T's, so information states, and there are certain update equations that I have omitted, but they are also essentially, you can be mathematically derive those equations to build this tree. Okay, so the optimization, because it's a tree, the optimization is also the Bellman operator. The Bellman operator will look a bit different. So before that, I would like to recall that the objective function has slightly changed. So it's now the value function of the states, but weighted by the beliefs of particular MDPs. So this is a value function for a policy for a fixed MDP, but then you weight it over the belief of that MDP. So that's this weighted value function is what is called as the belief value, Bayesian value function. And this is for a fixed policy, but then your objective is to maximize over all possible policies. So this is what we call the Bayes optimal value function, maximizing this Bayesian value function for all possible policies, where this value function is basically averaged. You can say the value functions are averaged over the beliefs. And we have a similar Bellman operator for this objective function. So we can do the same kind of tree building, tree search algorithm. So you start at the rightmost. So you always say that the value function, Bayesian value function at the end, and you just go back to the root. So in summary, what I meant to say is that, so if you know the MDP, you can do backward induction, but RL is with reinforcement learning is the fact that you don't know these mu's or you don't know the distributions. So what you do is you maximize the Bayesian objective function by maintaining a belief over the transition distributions. So you have a probability distribution over the probability distributions. Mathematically, this is a Dirichlet multinomial distribution, to be more precise. So you formalize this BAMDP, which is a large MDP, and the technique of solving them is same. But then what is the research all about? So in practice, what happens is that you cannot do backward induction because essentially the branching factors are too large. So computationally, that's the problem, and that's where most of the papers in Bayesian reinforcement learning are. So I can have a small break, and you can ask me questions, because if you're clear, then I can just go on to the main, like the current state of the art of things.
Will that part consider these computational issues?
Yeah, that part will consider the computational issues of the tree. So the algorithm is the same tree, expecting max algorithm on the tree.
I have a question regarding the prior distribution. Do you update this at each step, or the prior is kind of fixed and then only the posterior is kind of updated, like based on what you see? So essentially, what I mean to say is that, like do you take like each time you take like a mu from this prior distribution and then you multiply this with the likelihood, and then you do this like and then after that, do you also update the prior, or this is like constant?
Yeah. So what I take is closed form prior, so distant multinomial. So essentially, the prior becomes the posterior becomes the prior for the next step.
Okay, so it's sequentially updating like each step.
Yes. Yeah. The posterior is used as a prior for the next. Yeah.
Yes.
One thing I've been thinking about, I don't know if there's really a solution for it, but if you go back to the last BAMDP, this one. So if we look at the Bellman operator, so for all these uncertainty-based approaches or model-based approaches, I suspect there should be some way of actually removing the gamma, the discount factor. Because somehow gamma is there, at least in my intuition, is there to kind of, let's say, control for future uncertainty. And if we can model that uncertainty of the state transitions, that we should be able to figure out gamma by itself without actually having to set a fixed discount for it. Do you have any intuition around that, or seen any work in these uncertainty-based models?
Yeah, as far as I know, gamma is always there in this particular framework. So this is just one type of reinforcement learning algorithm, Bayesian. But people have removed gamma from regret-based algorithms like UCRL. And I mean, there are certain papers, not UCRL, but there are certain papers that do this for discount-free settings. Yeah.
Okay. All right. Thank you.
Yeah.
I have a question about, so this Bayesian RL is kind of a new concept to me. So I was wondering, the terms model-free and model-based reinforcement learning, how do they, if you see them as like two circles,
yeah,
and then this Bayesian is a third circle, if you will. Yeah. I mean, how do these relate? Is Bayesian RL a case of model-based RL, for example, or how does this connect?
No, I mean, if you have a Venn diagram for that, then Bayesian methods actually can be both model-based and model-free. The one I am talking about is model-based, but there are certain new methods. Particularly, there was one paper called Variational Bayesian Reinforcement Learning, something like that. If you search on Google Scholar, there are model-free methods doing the same Bayesian method. So the Bayesian part of it is essentially just maintaining a probability distribution over the possible MDPs in some way. But a perpendicular approach that people have taken is being Bayesian on the value function directly. So that's model free. So in that case, what you do is you are maintaining a probability distribution or belief distribution, not over the models that like I do, but directly over the possible value functions. And then the equation you can do is like a Bayesian Q-learning kind of thing. So people have done that. So that's model-free Bayesian. Yeah.
Thank you.
Do you have time for one question more?
Yeah, sure.
In such case, Antonio has raised his hand.
Yes, thank you. I wonder if you could explain me a little bit better how the algorithm with the belief work in practice. As far as I understood, you use this belief in order to allow for backward induction in the case that you have some problem in the underlying MDP.
Yeah.
So I assume also that when you assume this belief through time, it gets more accurate once you're using the current posterior belief will be the prior for the next one. Yeah. And given that the backward induction, it's something fixed in time. So I was wondering how this uncertainty of the belief is handled within the backward induction that you made available by using this. I don't know if Yeah. Okay.
Yeah, so you're right about the fact that the posterior becomes more sharper with time. So, but there are two basically in this. So I've emphasized more on the backward induction part, but there is a very important computationally in implementation wise. There is an important step that this tree is not given to you, and you have to kind of build this tree forward. So like you do in deep learning neural network, you go do a forward pass and backward pass. Similar to that, what you do is you are just given a starting root omega t, and you build this tree forward up to certain depth. And once you have built it, so you know the transition probabilities at each of these, you can say the edges, then is only when it's possible to do a backward induction. So, so those transition probabilities actually help, as you are saying, because they become sharper towards the end. I mean,
Okay,
yeah.
Yes.
I mean here, so this is the Bellman operator on the right, on the bottom left. So you see this transition distribution, nu of omega prime given omega and a.
Yes. Yes.
So this one's actually change as you grow the tree. Yeah.
Okay. Thank you.
So I can quickly go through our results. Not our results, but I want to explain you computationally and research wise what's the catch, what's the big, like where are the paper being published and why. So essentially is the computational factor, so the branching factor. So what happens is that on the left is you have full blown tree. So as I explained to you, you have to do a forward pass. So you start with omega t. So you go towards right and you keep storing all the nodes because you need them later for the backward induction step, which starts from right to left. But for that, you first need to build the tree and store it in memory. And that's expensive because it has a very big branching factor, and you need to, basically you need to do it for a long horizon or long depth. So if you consider this like a tree vertically. So what people have proposed is doing sampling. So simply people have said that, well, we can just remove the nodes that are less likely probable to be seen, because ultimately these nodes are being produced from a posterior distribution. So if there are some less likely information states towards the end, you just don't sample, you don't take them into account, which you can do essentially by sampling. So that reduces some amount of memory for storing this tree. Then people have done some more tricks involving some properties of the distribution, posterior distribution, which is basically bounding the possible the goodness of a particular node, because the goodness of a node is essentially the value of that node. So if it's the value will not be too useful for you, or it will not be too helpful at the root, because there is a discounting factor going through as well. So you just kind of remove that. So that's one way. And then there is the previous state of the art was Monte Carlo sampling. So here what they do is, instead of just sampling the information state nodes, they also sample the actions. So you can see the white ones are the ones that are sampled away. So I mean, they are not taken into account. So we just consider this violet part of the tree. So how do they decide on which action to take is using what is a heuristic, which is called upper confidence heuristic. And that you can significantly see between the slides that the size of this particular tree is much less than what we started from before, from a full blown. So that was the state of the art until last year. So then we had this paper in AI stats last year. So what we proposed is essentially something more interesting. So we said that instead of considering actions, so the squares were actions in the previous slides, if you know. But here for us, the squares are the policies. So what's the benefit of that is we generate policies. And since we have policies, we can, go forward quite deep into the tree without, branching too much. So we use this policy to go forward in the posterior by k steps. So k can be more than one. But in the previous cases, because they were just using actions, they could just go one. So essentially, we build a deeper tree. So the tree is deeper, but it's also sparse because we do a meta algorithm, and we don't consider the square nodes as actions but as policies, and we use them to do a k step where k can be 5, 10, 15. So that's where we do again the branching, and so the memory size is much less reduced, and you are still able to look too far in the posterior, because the gist of this doing all this in this setting is that the posterior, as somebody said, will converge. So if you can get to the converged posterior without spending too much memory, you can do a good approximation when you do the backward induction. So this is the generation part. So it's from this, it's going from left to right. Backward induction is a fixed algorithm, so there's nothing innovative about there, but just generating a a tree with less number of nodes. So this is like all this is basically saying the same thing. So we basically, from the current node, we sample certain policies, and we play them, or we forward the posterior for k steps, and then we do repeat the same process. So we have a theorem. Sorry.
Are these policies deterministic?
Sorry.
Are these policies deterministic?
The policies, yes. No, so, hold on. So it's yeah, it's deterministic. Yeah, the policy set for that we use is deterministic. Yes. Yeah.
And how do you sample them? Because I guess since you have a possibility for many more policies than single actions, doing sampling is quite important, I guess.
Yeah. So in this case, what we do is because these omega states have a set, what I said earlier was a belief state. So the belief over the MDPs. So essentially, when we use that belief to sample the MDPs, and we just take the optimal policy for each of those sampled MDPs. So it's like a multi-sample Thompson sampling. So we sample the MDPs first from the belief, and then we solve those MDPs using the backward induction and take the best policies, the best deterministic policies for those as the policies for generating future posteriors.
So you must have observed that exact policy than before. There's no way to generalize sub policies, if you want to call it that.
No. So yeah, of course, the policy set is much smaller, but the kind of bound you get is a bit different. But then the fact that you said that there is no way to see the policy before, yeah, first you have to sample the MDP from the belief, and then when you see the MDP, you find the policy.
Yeah, I was just thinking from if you have a very large state space, you can probably assume that some of the state transitions are very similar. So if you have a learned state transition function, I guess you have some possibilities at least to generalize parts of the policies. While in this case, you need to have observed the full policy before you can actually estimate the omega t plus k. Yeah,
you need that for the whole state space, or at least the the parametric policy. If you want to reduce the size.
All right, thank you.
How do you decide on the prior? Like, is it kind of you start with the uniform, or for any specific problem?
No, so for model based, it's always Dirichlet multinomial, because Dirichlet is a prior over probabilities. So Dirichlet is like the only prior over probabilities.
Okay, so you exploit the conjugate conjugacy here. Okay.
Okay, so we have this pack theorem, probably approximately correct. So theorem which says that the value function at the root for our algorithm, which is superscripted by ds, is bounded by the true value function minus some terms. So it's not very bad. But the memory is much better. So here you can see the sparse sampling algorithm, which just samples the states, has a memory which is exponential in the horizon t. But here we have the samples. So at the first in the constants, you can say in the pre-exponential terms, we just have instead of full action space, we just have the samples. if we take n policies and m samples for the next stage. But the most important part is that the memory is reduced, has reduced by a factor of k. So in exponential, you get much benefit overall in the memory, because you have reduced exponential, the main exponential factor by k. We do so by certain properties. So one is quite intuitive that many people said before, is belief concentration. So as you go over time, the belief concentrates. So the posterior concentrates. The other one is a bounded correlation thing, so that two similar MDPs will have higher correlation. So that's also very intuitive. And using these two assumptions, we have the result. More importantly, we tried this on all the benchmark algorithms that were, all the benchmark environments that were there with all the benchmark algorithms. And essentially, yeah, so this is the reward. So the numbers are basically total reward gathered over certain horizon ranging between 1,000 to 20,000 steps. But the main idea is all of them is like benchmark. So I used the same setting that were used in the previous 4 or 5 papers. So based on that, this is the first top 2 are our algorithms, Sparser. So I call it Sparser. But there are also 2 variants for that, because there is one step of policy generation. So for that policy generation step, you can either do a complete policy, find a complete good policy using policy iteration, or you can do, if your MDP is large, for large state spaces, you can use a approximate solver like RTDP. But all of them are plugged into this main idea of Bayesian tree, and then you get the results which are better than the BAMCP was the best one from Monte research. And these are the settings with Maze being the largest. And I also did it with the DQN, so bootstrap DQN and Thompson sampling. So these are important. So Thompson sampling is a model-free Bayesian algorithm as well. So that was also important to compare with that. And DQN, like deep learning networks are famous. So these 2 plots are for different horizon, and this is the regret here. So it's better to be actually towards the less part. So regret is good to have less and not to have more. So the brown one is for us, and you can see this one, BDQN actually performs bad in large states, even bad, worse than PSRL. PSRL is posterior sampling or Thompson sampling. Yeah, that's it.
Thank you, Divya. So we've already had a few questions. Do we have some more?
So for the benchmarks you had, I'm guessing they are relatively small state spaces. At least the grid ones are pretty small, I guess.
Yeah, the grid one is small. The maze one is big. Is I think around 90, 100 cross, like 10,000, I can say. Yeah, around 10,000 states.
Okay. And the action space is discrete.
Yes.
So would this work, this policy sampling, would that work for continuous action spaces?
Policy sampling would work for continuous action. So the difficult part is not continuous action spaces. That can be a quite easy extension. The difficult part is continuous state spaces. Yeah. So because I said here policy sampling, using PI or RTDP, so you can have this policy gradient for continuous. So you can have a policy which is coming from a parametric space, continuous policy, like a Gaussian or something, and then you can have you can, instead of doing policy iteration or RTDP, you can do this one, policy gradient, and get that policy and build the same tree.
Okay.
Yeah.
All right. Thank you.
I was wondering. Oh, sorry, I'm not.
No.
Yeah, I had a question about I mean, I don't very often stumble upon papers on Bayesian RL. I mean, I'm mostly in computer vision, for example, and there has been quite a lot of combining RL to solve various computer vision tasks and so on, and learning to navigate in large cities with street view, and you name it. all sorts of applications. I'm just wondering if Bayesian RL is sort of applied within such things, or if it is a little bit more theoretical in some sense, if you get my question.
Yeah, it is theoretical because this algorithm is for continuous, this is for discrete state and action spaces, and so it's not scalable. So for images, there hasn't been any useful Bayesian RL. There are some papers now recently for doing variational Bayesian reinforcement learning, but they are not good. So policy gradient is the way to go for images if you have images as input or continuous state spaces up to now. Yeah.
Yeah, thanks.
But I guess it's still used in multi-arm bandit settings, which you could argue is a special case of RL.
Yeah, definitely. So theoretically, you have so policy gradient. You cannot get much. Just recently, now there has been some regret bound for policy gradient, but it's much easier to get regret bounds or certain theoretical bounds for these cases. Yeah. There are theoretical interests. So the main fact being the main point being why are we doing research on this is because reinforcement learning is not just acting in an environment. So you can have a function approximator like a neural network, which so if you give enough. So what's the difference between sequential decision making and supervised learning? Supervised learning works in the limit of the data. Reinforcement learning promises that it will work in finite sample data, or use as less samples as possible to get a good output. That has not been the case yet with the DQN or something like that. But the other way, as you are saying, multi-arm bandits and so on, they have the algorithms that we have now, like UCRL, which are theoretically very good. Theoretically in the sense that with less samples, they find an algorithm that maximizes the long-term reward, but they don't scale well. So there is still a gap between the algorithms that do theoretically sound and the algorithm that actually work. So there is a gap.
So you mentioned that the variational approaches, they are not maybe that good, the one that have been proposed so far. What do you think is the reason? Is it maybe that the distribution, the complexity of the distribution that tries to approximate, or there is something more in the construction?
Can you repeat? So did you say something about variational?
Yeah, so, I heard that. You mentioned that this variational approaches, variational based approaches.
Yeah.
Did you mention that they are not maybe that good right now to solve these kind of problems, for inference? When you talk about inference in such models.
Yeah, the fact that I in my own experience I believe it is that the inference has to be very good. The variational inference might work, but not Monte Carlo. But the paper that I was talking about was doing variational inference with model free. So in RL, what happens is the model-based methods are always working much better than model free. So they were doing variational with the model free. But if you try out, yeah.
Okay. Thanks.
Yeah.
Great. If there are no more questions, I think we should thank Divya for a really nice presentation. And everybody will come back next week, the 27th of May. We'll have Alireza Salehi talking about biochemistry and metabolomics. So thank you all for today.
Thank you.
Thank you.
Bye-bye.